Today we will continue with waves, and specifically we're going to begin talking about string waves. Waves on a string, waves on a spring. We're going to look at how they reflect off of a boundary or a barrier. We're going to describe what wave interference is. We're going to calculate the amplitude of two waves that interfere both constructively and destructively. We're going to find the frequency, velocity, or wavelength of a standing wave on a string, and we're going to talk about harmonics for a string. That has more to do with standing waves too. So just to reiterate a point, waves for us are a traveling energetic disturbance. An energetic disturbance moving through a medium. So, for a wave on a string, our medium is going to be the string, and our energy is going to be us flicking a pulse into the string that moves down the string. So, let's get into it. String waves. Places we see string waves the most is string instruments and bridges. If you get a free minute, look up Galloping Gertie. It's a bridge that got some waves on it and fell apart. It's actually pretty incredible to see wind do that to something, but we don't have time to show you that here today. Just as a review, we've got amplitude and we've got wavelength as our two big measurements for the thing. The wavelength being literally the length of the wave, and the amplitude being the thing that tells me about energy. And for string waves, think of it this way. I have to hit the string much harder to get a higher amplitude, which means I'm doing more work on the string, or I'm putting more energy into the string. Wavelength, again, length of the wave. And remember, the way that we're going to talk about this is it's the wavelength that depends on the velocity and the frequency. The velocity doesn't depend on anything but the medium, and the frequency doesn't depend on anything except for the source. Changing the velocity will not change the frequency, and changing the frequency will not change the velocity, but both of those things will affect the wavelength. The only way to change the velocity is changing the medium. For a string, it's making it tighter or looser, and that's what you guys do with your stringed instruments. And the only way to change frequency is by somehow adjusting the source, getting something else that's going to cause our object to vibrate. So, string waves. For wave reflection on string waves, just to look at what's going to happen, we're going to send this wave down, and it's going to hit the barrier right here. And when it hits the barrier, it's going to bounce back, but something's going to happen to it when it bounces back. So here comes the wave, it hits the barrier, and it bounces back. Now, what happened there, it went from being phase up to being phase down. When a wave is reflected, when a string wave is reflected off of a barrier, we're going to see what we call a phase shift. We can look at this in class with the springs, but as that wave hits a barrier, because this end is not free to move, the thing swings back out of phase. Now, that's really all there is to wave reflection for waves on a string. When they hit a barrier, they come back out of phase. We get wave interference when two waves in the same medium meet. They're going in opposite directions in the same medium. Now, when they hit, they do not affect each other. But what they do is affect the medium. I just have two different waveforms here. I've got the triangle waves and the sine waves. But when these two things hit, remember they're just traveling on a piece of string. They're going to lift the string up an extra amount. And so when these two waves are in the same place at the same time, we're going to see a bigger amplitude. This is constructive interference. These waves are adding together when they hit. So here we have the waves add. The amplitude of the waves add up. We get a bigger wave than we had before. So let's see if we can make this work. Yeah. So looking at how these things go, when these two waves come together, we see their amplitude add up for a moment, right when they're touching, and then they pass through each other unaffected. Same thing over here. When these two waves meet each other, and they're the same size, we see their amplitudes beginning to add, and we get a huge wave, and then they move apart unaffected. That's wave interference. We can do the same thing with destructive interference. This time I have two waves that are out of phase that meet each other, and when that happens, their amplitudes still add, but because one of them is negative, they tend to cancel each other out. So in this case, right here, when those two things are together, they add and they cancel out. Same thing with the triangle waveforms. When these two things come together, we see the positive amplitude and the negative amplitude add together and they cancel out. So in destructive interference, the amplitudes cancel, because waves are out of phase with each other. This is all pretty easy. Okay, they don't affect each other, they affect the medium, and they pass right on through each other. The reason this is important is because of standing waves. When you have a standing wave, you have two identical waves, the wave on top and the wave on the bottom. The only difference is that they are traveling in opposite directions. So, what we see with a standing wave is that when they're in the same spot, when I have two in-phase places together, I get a big disturbance. And as they move and become out of phase, that goes down. So what we have here are these two waves constantly having constructive and destructive interference. This would be constructive, that would be destructive, constructive, destructive. This is a standing wave. This is what we see in strings. This is how your string instrument works. You set up a standing wave in your object. So we're going to look at the parts of a standing wave. This is called an antinode. It's the place in the medium that is vibrating the most because of the wave. This is a node. There is no movement, or very little movement at the node. That's how we know. Antinodes are the places where we see the constructive interference when they're in the same place. A node is always going to not move. An antinode is also where you're going to see the destructive interference when this part of the wave and this part of the wave are in the same place. But these two waves are constantly passing in front of each other, which is why we get this happening in the medium. So, this is the interference between two waves traveling in opposite directions. Okay, standing wave is the interference between two waves traveling in opposite directions. And we'll play with some of those tomorrow in class. The reason this is actually kind of fun is because we can do harmonics with a standing wave. And harmonics come up in instruments all the time, even with brass instruments and things like that. So what can happen is, let's pretend this is my length of string right here. It can vibrate multiple ways. It's going to be a forced node on each end, though, so there's not going to be any movement there. Now, I can have half a wave, right? This is half a wave. I can have a whole wave. I can have 3 halves of a wave. I can have 2 waves. I can have as many as I want. This is our first harmonic. This is our second harmonic. This is our third harmonic. This is our fourth harmonic. This is our fifth harmonic. Now, because this is a set length, what we can do is find out what lambda is equal to. I know that half a wavelength is equal to L, so lambda is going to be twice the length for my strings. Here I know that lambda is equal to L. Here I see that lambda is going to be equal to 2. So I see that 3 halves of a wave, 1, 2, 3 halves of that wave give me 2/3 of a length for lambda. When I have 2 on here, I see that lambda is equal to that length over 2. So, looking at this, I know that these are my lengths for the various harmonics. You can figure out 5 on your own. But looking at this, since I know that lambda is equal to velocity over the frequency, each time I go from one harmonic to the other, lambda changes. As that happens, we have to ask ourselves, is it the frequency that's changing, or is it the velocity that's changing? Well, it's pretty easy. I'm not changing the medium, so the velocity is constant this whole time, but it's the frequency that's changing. So what's happening, as I go from the first harmonic to the second harmonic, I am halving, okay, from 1 to 2, I am taking lambda and I'm dividing it by 2, which means that my frequency doubled. And looking at frequency 1, okay, so this is twice the frequency. If I look at this, I'm halving it again, and as we look at the next one, see, this is half of lambda. This is actually going to be 1/3 of what we had before. So going to the third harmonic, I have 3 times the frequency. Going to the fourth harmonic, I have 5 times the frequency. As we do this, we are increasing the frequency by 2. I'm sorry, fourth harmonic is 4 times the frequency. We're increasing it by 2, 3, and 4 as we go on. For music, these are octaves. We'll play with this in class tomorrow as well. So that's it for waves on a string. There's a lot that we can do with this, so we'll spend a lot of time working with it.